Alright, grade 9s. Hello, cohort A. Hope you're having a lovely Monday morning, or Monday afternoon now, I guess. Alright, so I'm going to keep this pretty short. I showed the cohort B, all the demos I showed you guys on Friday, except the sodium and water. I'm going to save that one. Alright, so listen, before we move on to anything else, I just wanted to point out the handout I gave you on paper, okay, on Friday, had there's 2 pages of density questions. There is a 3rd page posted on OneNote, so can you please make sure you do that if you haven't done it already. I know cohort B kind of did it already. There's 7 questions on that page, so just make sure if you look at the density that you do all of the density homework that's listed there. Okay, and we'll start with that. Now, after that, density lab. So in class today, we measured the density of some blocks. So I'm just going to take you through the measurements. There were 8 blocks in total. Okay, so I didn't label them all here, but there were 4 plastic blocks, and there were 4 metal blocks. And so for the metal ones, we're going to do something a little special with them. But just let me take you through the measurements. So we'll do that first. Okay. Yeah, we had 4 blocks. The first one was iron, so block A was iron, and then there was aluminum, and then brass, and then copper, okay? And what we did was we measured the dimensions. All the blocks are cubes, and all the cubes are 2.50 centimeters on each side, okay? Now you can use that to calculate the volume, but since all the cubes are the same size, you'll only have to determine the volume once. And you do that by just multiplying length times width times height, or taking 2.50 and just going to the power of 3. All right, they do have different masses, so I brought in a scale today. We measured the mass of all 8 blocks, okay? The goal of this experiment, the purpose of this experiment is to determine the density of the different materials. So all we have to do is divide the mass by the volume, and we'll get the density in unit of grams per centimeter cubed. So we did an example for you here to get the density of the iron block. First, we found the volume, and so we found the volume just by multiplying length times width times height, and you get 15.625 cubic centimeters in every single case, because all the blocks have the same dimension. So then we measured the mass. The mass was 126.3 grams, pardon me, for the iron block. So when you divide those 2 numbers, you get 8.0832. I was telling the students in class, you cannot keep all 5 of those digits. If you look at your measurements, the ruler that we use to measure the dimension of the block reads up to the millimeter mark, or fractions of a millimeter, I should say. So we have 3 digits of precision in that number. The trailing 0 was actually measured, was right on the dot, 2.5. Okay? If it wasn't, I would write 2.51 or 2.52, you know, that kind of thing. But it was right on the dot, so I wrote 2.50. So there's 3 digits of precision there. Okay? And the mass has 4 digits. Okay? When I do a calculation to find density, my answer cannot have more precision than my measurements. And so this number has 5 digits in it, but we have to round it so that it only has 3 digits of precision. So I round it to 8.08, okay, grams per cubic centimeter. We'll talk more about precision and what's called significant digits another time. Okay. All right, so I want you to finish the table, so you to fill this in by calculating the density of every block. Okay. After that, so this is part of the homework. So it says, in the homework it says do the lab calculations. This is what I want you to do. Okay, so after that, you're going to come down here for the metal blocks, and only the metal blocks, not the plastic ones. You're going to look up the accepted value of the density of the blocks for comparison purposes. Okay, and the way you do that is you use this calculation here, okay, the percentage difference, and the percentage difference is equal to the measured value minus the accepted value times 100%. Or sorry, divided by the accepted value and then times 100%. Now you have to Google the accepted value. So for example, what you do is, if you're wondering what the density of iron is supposed to be, just Google it. What's the density of iron? Make sure the units that you find online are in grams per cubic centimeter. Okay, we did it here for aluminum. So if you Google aluminum, you'll find that its density is 2.7 grams per cubic centimeter. That is the accepted value. But the measured value that we got was 2.8 grams per cubic centimeter. So it's not perfect. Our lab results are seldom perfect. There's usually a small deviation in the measurement. So to figure out how big that deviation is, we measure here, let me rewrite this, the percentage difference. Okay, and what we did is we just subtracted the two numbers. So we use the formula that's above here, that formula that's in the box at the top. You take your measured value, which is the red number here. You subtract the accepted value for the density of aluminum. You divide by that accepted value. So you make sure you do the subtraction first, then do the division, then times it by 100%. And we ended up getting that the percentage difference was 3.7%. That's pretty close to, that's pretty good actually. Okay, we're less than 5% away from the correct answer. And you know, errors can happen for a number of reasons. It could be our scale's a little off. It could be that our measurement with a ruler had a small error in measurement in it. Okay, it's only 2.7 centimeters. So if you're off by one, you know, like not centimeter, but if you're off by 1 millimeter, let's say, you could have a small deviation in the answer, right, of 1 or 2%. Okay, so anyway, that's how you find percentage difference. I would like you to do that for all three of the remaining metal blocks, so the iron, the brass, and the copper blocks, okay, and determine the percentage difference. All right, so that takes care of the lab calculations and the density lab. Let's go to a new topic here. Okay, so there's a couple other things I want to discuss. Won't take very long. Okay, one of those things is, and I really didn't get to mention this to cohort B today, but I need to mention it to you. It came up in the homework, and I think I just have one of my homework pages out of order, so I apologize for that. Ions. Okay, let's just talk. I was going to put something else, but let's just put ions. Okay, what is an ion? Well, it is an atom or molecule that has gained electrons, okay, or lost electrons. Now it's never an all or nothing thing, unless you're hydrogen, you know, like sometimes they lose them all. But in this case, most things don't lose them all, but the valence ones, typically those are easy to lose and gain, okay? I'm getting a lot of notifications here on the thing. I'm just going to silence that for a moment. Okay, so here's the deal. If you gain electrons, actually I'll start with losing. If you lose electrons, okay, the atom or molecule will therefore have a positive, put a little plus like that, charge overall. And the reason why is because if you lose negatives, normally these things are equal, but if you lose negatives, okay, you're going to have an overall positive charge. So in a neutral object, the number of positives and negatives equal. Okay, but if you lose some negatives, now you're going to have a positive charge left over. These positive charges, these positive ions, are also known as cations. One word. Okay, not cations, but cations. All right, now if you gain, okay, the atom or molecule will now have a negative charge overall. Okay, and these are AKA dog ions. No, I'm just kidding. You were thinking dog ions, though, cat ions and dog ions. I know what you're thinking, right? Not a dog ion, guys. It's actually called an anion. Okay? Anions. I should pluralize it like that. Now, here's a little assignment for you. Just very short, only take a minute. What is an on ion? Okay, an on ion. I'll give you a bonus mark if you can answer that. The first person to give me a logical answer. What is an on ion? All right, so now you know what an ion is. An ion is an charged atom or molecule, right? And the way you get charged is you either gain electrons to become negative, those are anions, or you lose electrons to become positive, those are called cations. Okay? Now, generally speaking, metals, they like to lose their valence electrons to become stable. And therefore form cations. Non-metals, on the other hand, they like to gain valence electrons to complete the shell, and therefore form, they tend to form anyway, anions. Okay, a great example of this, I'll just give you an example, and we're going to talk a lot more about this tomorrow for you, but I'll just give you an example of this today. Sodium has one valence electron, and it really doesn't want it, okay, it wants to get rid of it. Chlorine, on the other hand, has 7 valence electrons, right? And it's missing one. I'll put a little X where it's missing one. It would love to gain another electron. So when these two guys get together, what will happen is sodium will happily donate its electron to the chlorine, and now they're both happy. And what happens is the sodium will now have a positive 1 charge, and the chlorine, with its full outer shell all around it, has a negative 1 charge. So this is the cation and anion, right? And we call this sodium chloride, we call it an ionic salt. Okay, ionic because the atoms consist of ions embedded in the salt. Sodium and chlorine ions, right? The sodium positive ion and then the chlorine negative ion. All right, so there you go. Now you know what ions are. You know what cations are. You know what anions are. Okay, and they're just charged atoms or molecules, right? And you know how they do that. They do it by gaining or losing electrons. You can't gain or lose protons, by the way, because protons are bound in the nucleus, and they cannot be, the only place you could gain or lose protons would be, say, except for some of the heavy elements, but like for normal elements we see all around us, the only way to add protons to it would be inside a star at 15 million degrees Celsius or more in order to fuse those protons into the nucleus. Okay, to split an atom would be just as difficult, right? So maybe inside a star there's enough energy to split an atom, okay, and remove protons from the nucleus. But under normal conditions, at room temperature, in the classroom, and anywhere you go on the planet, that doesn't happen. All right. Now there are some radioactive elements that do have, like americium, a very heavy element on the periodic table, will lose protons and neutrons in a process called alpha decay. But we'll talk more about those things in a future science class, okay? All right. Now let's move on. and let's talk about some trends on the periodic table. All right, here's the deal. Okay, so we've already talked about how the valence shell determines the chemical properties of the group, right? So if you're an alkali metal, you have 1 valence electron. If you're an alkaline earth metal, you have 2. If you're in the transition area, you typically have 2, 3, or 4, you know, that kind of thing. That's a bit complicated, that area. Aluminum, though, has 3. The metalloids, depending on what row you're in, but like, you know, they could have 3 or 4 valence electrons. Then non-metals will have 5, 6, or 7, and the noble gases have 8, which makes them a full shell. The exception being helium, because it's in the first row, it only has 2 to form a full shell. But the number of valence electrons you have determines your character, okay? Your chemical character, your chemical properties, okay? Like, for example, sodium reacts with water to release hydrogen gas, okay, and form sodium hydroxide in the water, and it's a very explosive reaction. That's a chemical property of sodium. And why is it like that? It's because it really desperately wants to get rid of that valence electron that it has, and so it's very reactive. Okay. Anyway, metals. Metals generally have low numbers of valence electrons. 1, 2, 3, that kind of thing. When metal atoms bond to each other, they release their valence electrons. And I mentioned this today. I put an additional video online for you. Okay, it's only a 5-minute video maybe, and it explains something called metallic bonding. But it's kind of cool how it works. I used Rice Krispie squares, and the students today had Rice Krispie squares. It says, when metal atoms bond to each other, they release their valence electrons. I'm going to circle this in red. They release their valence electrons, okay, they release them, so that it forms a negatively charged glue that surrounds and binds the positively charged cations. So like the metal atoms that have liberated their electrons, now they're positively charged, but they're surrounded by this sort of soupy sort of glue of electrons that surrounds them. Okay, we call it a sea of electrons, like a sea, like an ocean. Okay, and that bonds the positive charges. So negative and positive attract. So it's like the atoms of metal are like this positively charged atom sort of sitting in a negatively charged soup. So they're stuck in the soup because it's negatively charged and they're positively charged. And a great example of this is Rice Krispie squares. Okay. Rice Krispie squares, the Rice Krispies are held together by a glue of marshmallow, okay, of melted marshmallows. And those marshmallows are like the electrons, and the Rice Krispies are like the metal atoms. Okay, it's a kind of a neat analogy. So, how does this explain the properties of metals? Well, why are metals good conductors? Well, if you're a good conductor, it means that electrons can move more easily through you. Well, if you have a loose hold on your valence electrons, and they're sort of floating around there in the sea of electrons, well, they're easily moved. And so when we give them a little push, they'll start to flow through the metal, and that's conducting electricity. So that's why metals are good conductors. They support the flow of charge. The soup can flow, a negatively charged soup. Now, they have high melting and boiling points. Okay, so this high melting and boiling points business, that's because they're bonded together in the soup, right? So think of a Rice Krispie square. It forms a solid, okay? And the solid is, you know, like it's got some solid sort of structure. It takes some force to pull it apart. So with the electrons in the metals, the negative soup, the pull is even stronger. And so they have really high melting points. It takes a lot to pull those metal atoms out of that soup, okay, to make them melt and fall out of their lattice work. Okay, so that's why they have high melting points and even higher boiling points, of course. Okay, so think of, like I said, think of the Rice Krispie squares. The marshmallow glue binds the crispy bits together, making the square pliable, malleable, and ductile. Okay, so that is other properties of metals. Pliable, malleable, and ductile. Okay, so luster. The negative sea of electrons, or the negative glue, electron glue, repels light waves for reasons that we'll discuss in future science classes. That makes them shiny, so they have high luster. So you see, we get it. we get what's happening inside the metal. We get why metals are bendable, and we can form them into various shapes to make various tools and pipes and everything else. It's all about this sea of electrons. What makes them good conductors of heat and electricity, what makes them shiny, what makes them malleable. It's all connected, okay? And it's a great way of thinking of it is the Rice Krispie square. Now, the chemical properties we talked about already. We already said that atoms like to have a full shell, and so they want to, for metals, you want to empty that valence shell and expose that full shell underneath. So what they do, especially the alkaline metals, particularly like this, is they'll donate their valence electrons to other atoms, and when they do that, we get a chemical reaction. Like, for example, when you throw sodium in water and it donates its electron to the water molecules, it actually breaks the bond between the hydrogen and oxygen in the water, and it releases the hydrogen gas, okay? So that's how aggressively sodium donates its electron to the water. It's like it throws an electron at it so hard that it actually breaks the bond that holds the hydrogen to the oxygen in the water. Okay, if you have more than one valence electron, though, you tend to be less reactive because it's kind of an all or nothing thing. You have to give all your electrons away. So if I throw, for example, a piece of calcium in the water, maybe you'll see a small amount of hydrogen being produced, but not as much because it's more difficult for the calcium to give away both its valence electrons to the water. So the more electrons you have, the more difficult it is for you to react with other things, okay? Because those other things have to accept your electrons. If you have too many to give, they won't just accept some of them. It has to be an all or nothing thing, and that's why aluminum, with 3 valence electrons, is actually pretty inert. I mean, it barely even rusts. Okay, Okay, so that's the difference between the various metals. So that's what I said here. If you have 2 or more valence electrons, you tend to be less chemically reactive because donating multiple electrons is more difficult. Okay, and that's why metals like aluminum and copper and zinc and nickel and so on tend to be less reactive, okay? Not unreactive completely, but less reactive. Like they don't explode when you throw them in water. In fact, they can't even break the water molecules bond. All right, let's talk about nonmetals. Now, nonmetals are basically everything that metals are not, right? So they're poor conductors of heat and electricity. They have relatively low melting and boiling points. Many of them are gases at room temperature. So that means that the boiling point would be well below room temperature. In some cases, like the noble gases, their boiling points could be almost absolute zero. Like I think helium boils at like 4 degrees Kelvin, which is close to minus 270 degrees Celsius. All right, so nonmetals have strongholds on their valence electrons. They don't want to give them up. In fact, they want more. Okay, that makes them very different. They don't have the negative C to bond them together, and that's why they have low melting points and boiling points. They don't tend to form solids very well. Now, not always. Like carbon would be an exception. So if you have lots of valence electrons, it's a little different. You're almost close to the border, right, between metal and non-metal there. So, all right. So, many nonmetals, especially the noble gases, have weak forces bonding them together. And therefore, that's why they have low melting and boiling points, okay? Now, they're not shiny. They tend to have a low luster. So, like, think of a piece of coal, right? Carbon is not exactly shiny, okay, as a lump of coal, okay? There's no negative C of electrons to repel the light, so they have low luster. That's why they have low luster. They're poor conductors because there's no sea of electrons that can move around easily, right? And they have a strong hold on their valence electrons, so the electrons can't move very easily. That makes them poor conductors of electricity. Now, the halogens are the group of nonmetals that are extremely reactive. The smaller they are, the easier it is for them to take electrons from other atoms. Okay, that's why fluorine is the most reactive of the reactive nonmetals. Okay, for the other nonmetals, they tend to be less reactive as it's more difficult to gain more than one electron. That's why carbon, which has 4 valence electrons, it's basically in the middle of the row on the periodic table, it's hard for it to gain 4, and it's hard for it to lose 4, so it tends to kind of be unreactive. Okay? But carbon does form bonds and forms many useful compounds, okay, that we find in nature, so yeah, especially in living things. Okay, so noble gases, of course, tend to be completely unreactive because their outer shell is full. Now, I showed the students this earlier today. This is kind of like a little bit of enrichment for you. This is called atomic radius, like how physically large, how much volume does the atom take up? Now remember, we're not talking about the nucleus. The nucleus is the smallest part of the atom by far. It's mostly empty space, right? So when we say radius, this is the electron cloud that surrounds the atom. That's what we mean by radius. How big is that electron cloud? It's almost like by measuring our solar system, let's say, you measure it all the way out to the Oort cloud, which is like this debris and dust, okay, way out there at the very edge of our solar system. Okay, so for the electrons, we're talking about how far away those valence electrons are from the nucleus. That's what we mean by atomic radius. Now, what you'll notice is if we go in the first element here, like hydrogen, in the first row, we'll notice that helium is smaller. Okay, now the reason why helium is smaller is because it has an extra proton in the nucleus to pull its valence electrons in closer. Positive and negative attract. So the more positive charge you have, okay, the more you're going to pull on the valence cloud and bring it close to you. Okay, so that's why helium is not, it's heavier than hydrogen, but it's also smaller in size. So it's in a way a more dense atom. Okay, now if you go to the next row, if you look at lithium, which I circled in red, okay, so here I'll color it. This is lithium right here. This guy I just colored in blue. That's a lot bigger than helium. Okay, all of a sudden it gets really big. Well, that's because we've added a valence shell. So now there's a full shell underneath, and you see electrons repel other electrons. So the full valence shell underneath the one valence electron that lithium has repels the valence electron really far away. And that's why lithium is so much bigger, okay, than helium. And then beryllium gets smaller because we're adding positive charges again as you move across the row. They get smaller and smaller and smaller as you go this way, because what's happening is you're increasing the positive pull of the nucleus, but the number of shells isn't changing across the row. And then once you get to the next row, the third row, all of a sudden it gets bigger again with sodium. Again, now we filled up a shell, we're adding an extra shell. Okay, and as soon as you add an extra shell, the atom gets bigger. Okay, the radius gets bigger. So the alkali metals are the biggest elements in every row, and they're also, the bigger you are, the easier it is for you to lose your valence electron. That's why you get more reactive as you go down this list. Okay, now as we move across the row and the positive charge from the nucleus increases, what happens is now when we get to the nonmetals, they want to hold on to their electrons. But fluorine is the smallest reactive nonmetal. Remember, the noble gases are not reactive, so fluorine is the smallest reactive nonmetal. It wants one extra electron, and the smaller you are, the easier it is for you to gain an extra electron, which is why fluorine is the most dangerous halogen. See, it's kind of the opposite, right? If you're big, it's easy to give away a valence electron. If you're small, it's easier to gain one. Okay? So fluorine is reactive for exactly the opposite reason that, say, sodium is reactive. One wants to lose its electron, the other one wants to gain. Okay? If you're gaining, it's better to be small because the positive nucleus is in the center. So it's easier for it to attract another electron. However, if you're losing, it's better to be big. And that's why cesium down here and francium, which is not shown in this picture, would be even more reactive. All right, so there's one more thing I just wanted to show you, and then we'll be done with this one. So I'm at a half hour now. I'm going to try to keep these videos quick and short. All right, so take a look at this. Here you have diamond, graphite. amorphous carbon, graphene, we have Buckyballs, we have nanotubes, and so on. What do these all have in common? They are all different forms of one element on the periodic table, one very special element that's very versatile this way, carbon. Carbon forms many different useful compounds. So did you know that diamond is pure carbon? Pure carbon. A lump of coal is pure carbon. Well, diamond and coal, the same element, right? So it's kind of cool when you think about it. This is what the lattice work looks like. So these are all little carbon atoms here. The sticks in between them represent covalent bonds. Okay, so covalent means they share their electrons. Okay, and form this. So that's a covalent network. Okay, of bonds there. That's diamond, the hardest known, one of the hardest known substances, right? Graphite and graphene, the carbon is formed into sheets. Okay, so if you buy a graphite hockey stick, the graphite sheets are made of pure carbon. They're flexible and light. So lighter than wood and more flexible. Okay, and that's why graphite, like I think my bike is made of graphite, and it's very light. Okay, and it's fairly rigid. But you can make it with flex in it, depends on how you manufacture it. So graphite, very useful for making racket sports and various other things that we need to be light, and we need to have strength in them at the same time. So amorphous carbon is like a lump of coal. Okay, and the carbon looks kind of like this. It's a little more disorganized. Buckyballs is kind of a recent invention where you can put the carbon atoms together and form what looks like a soccer ball. Okay, you can actually put stuff in the soccer ball as well, but I'm not sure what they use them for, but anyway, they're called Buckyballs. And here, a nanotube is actually carbon atoms arranged in such a way so that they form a tube. Okay, and this would have various applications in technology. So anyway, I wanted to mention to you the different forms of carbon because it is going to come up in the homework, and that's it. Now, speaking of homework, I'm just going to finish it off. Here's what we decided today in class. We are going to cancel this quiz. Okay, we already had our element quiz. That was lesson 7. We had that up here. Okay, yeah, and we did density, we did patterns on the periodic table. That was today. So this is your homework today. Okay, as well, make sure you finish all the other homework. So we're on lesson 9. We're going to cancel the review and the quiz that went with it because there's not much left in chemistry, to be honest with you. There is only a couple of lessons left. Okay, and by the way, yeah, anyway, I'll tell you about the homework later, but yeah, there's only 2 lessons left. So we might as well just do those 2 lessons, and then we'll have a final test in chemistry, and then we'll move on from there. There's still lots to discuss in chemistry that I haven't discussed with you yet. So there's some important lessons coming up. I think if I was to estimate when we'd have a test, I only see you twice this week. I would say, I think I see you Tuesday and Thursday this week. But next week, Monday is a holiday. So I will see cohort B on Tuesday and Thursday. And I will see cohort A, which is you, on Wednesday and Friday next week. So Friday at the earliest we'll have a unit test. Next Friday. Okay, so, but it could be the following week. We'll see how far we get. Okay. All right, guys, so I hope you enjoyed that video, and we will talk to you soon. Okay, bye-bye.